Thanks, Shaheen. Okay, so the talk, the project I am undertaking at Pitt are sort of ultimately under the umbrella of the Beyond Spacetime project, which let's say, collaborator, conspirator, maybe are the words Chris was looking for earlier. This is a project generally on the emergence, and I put scare quotes around there because part of the project is, what does that mean exactly? The emergence of space-time from less than fully spatiotemporal physics. And I refer you to our website to see more information about all the work we've been doing on that for about 10 years now. The current phase of that project turns the focus on cosmology and quantum gravity in particular. And specifically in this series and this talk, the focus is on the question of before space-time. And the question might be put in general terms about whether there was a transition in something like the history of the universe from a state that has no effective classical space-time description to one that does at the Big Bang. And what are the implications of that? Okay, that's the general sort of topic that we have here. These are to be questions that will be addressed in a quantum gravity formulation of cosmology. I'll footnote an early paper by Vas sort of on this topic, which I wasn't aware of until we've been working on this for a while, but that does also is the first thing I find in the philosophical literature that tries to ask these questions. There'll be references, a page of references at the end of the talk. So, what kind of questions would come up in this scenario? So, what questions about such a transition and non-spatiotemporal states? You can see the question is already sort of tortured. I have to use temporal language to talk about something that would be non-temporal. But questions are going to be, what are the non-spatiotemporal degrees of freedom? How do they form in a sort of dynamical, again, quasi-temporal sense? How do they come to gather together to form space-time, if I can use that language? But then what are we supposed to actually make of the even language that I'm using there? How could there be such a thing as a change without time? How could there be a before and after? How could there be a process with some sort of causal, maybe, connotation involved? But the question I've talked about these in talks previously, today, and indeed in a paper with Chris, the focus I want to put on today is how there could be empirical laws as a general question governing such a process. So that's what I want to focus today. Okay, so I think this will be a matter of relief for you. The talk I'm going to give today is actually a truncated version of a slightly longer talk, but when I was giving a practice version of the talk to my student, Naranja Warrior, last week or earlier in the week, it became clear that it was too long, and she strongly advised me to cut a section out of it. This was a very painful process for me, but I think she was right. And so I hope I'm going to cut a section out. You will find it actually in the handout in case you're interested. I'd be happy to talk about it, but I'm not going to talk about it today. And in the hope that I can keep things in the time frame and not talk too go too fast through important ideas, I'm going to skip that section and go straight to the philosophical interlude. So the general outline is I'm going to give some philosophical framework, which I think at the end you may feel is in the form of philosophical platitudes, but I want to use those to emphasize a point about laws. Then I'm going to talk about what I think is the most sort of really interesting thing here, the idea of group field theory and the idea of geometrogenesis, so an approach to quantum gravity, and the idea that there might have been such a thing as a creation of space-time. And then I'm going to return at the end to tie those two parts together and address the question of laws in the context of group field theory in particular. Yes. I see the question from Lee. I was just sort of waiting for that. So this is something that will sort of be addressed later, but in fact, the theory, the framework I'm describing today, I think is sort of, the philosophical framework is general enough to consider contexts both where time itself arises and where time is sort of assumed to be there in the background all along. So not going to be getting specific, well, in the philosophical section, not going to be getting specific. So yes, so the group field theory, well, you'll see what the answer to the question is there. And I also see not everybody can see the questions I'm being asked. I think you may have the choice to pose questions to panelists and attendees so everybody can see it. But Lee was asking whether whether I'm including the hypothesis that space is emergent but time is fundamental. Okay. So let's turn to laws in space-time. So let's just set up some some background sort of stipulations and basic ideas. So this is maybe for philosophers, but when one talks of laws, it's often thought, you can either be talking about some, gnomic fact, or you could be just referring to the statement describing that fact. When I use the term law, just for reference, I'm referring to the statement itself. So for instance, Newton's laws, perhaps, the actual statement of those. We also sometimes call some mathematical truths laws, but I have in mind empirical laws, which we usually think of as being contingent rather than mathematical truths. And the key property of laws that I want to focus on is what Feynman, in the Character of Physical Law, calls their universality. And there's a nice quotation that I like that he gives there in those lectures, where he says, nature uses only her longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. Okay, this is the end of a chapter discussing the law of gravity and Newton's laws of gravity, and a nice discussion of how observations of the solar system, the small pieces of the fabric, can actually be extrapolated to universal gravity and still seen to hold, of course, modulo general relativity, at ever increasing cosmological scales. That's the example he's talking about, and so he's making a point about induction, but he's also making a point about the nature of laws, namely that they express regularities. So I told you these were going to be some platitudes, but laws, of course, express regularities in events. So each small piece, in that sense, looks like the whole. If I find a regularity in some part, it's a regularity of the whole in this picture. Okay, so that's the point that I want to focus on here, and it's that role of laws that I want to emphasize. So I'm going to there are many philosophical accounts of what else laws might do. They might express best systems, they might express relations between universals, and they might say express some primitive kind of gnomic necessities. So somebody's asking if I mean empirically confirmed laws. I mean empirically confirmable. So I really mean to distinguish them from, in a sense, from mathematical truths. You'll maybe see why I wanted to add another word other than contingent later on in the end. So, but I mean, the things we think of as natural laws of physics as distinct from mathematical truths. So if the question has in mind, are the laws that I'm going to consider today, are they already empirically confirmed? Then probably not, or only very mildly. So I'm going to consider laws that might be empirically confirmed. Okay, so with all that said as background in the concept of law, I want to distinguish two ways in which laws depend on space-time. So two kinds of issues that might arise for non-spatiotemporal laws. So the first thing is the most obvious fact that some laws explicitly state regularities in space-time terms. but some do not. So of course, many of the laws that when we think of laws in physics, many of them, characteristically say might be differential equations with derivatives of time and space, and they're equations for functions over time and space, and a law like that then states regularities, and its regularities literally in explicit space-time terms. But of course, not all laws are like that. And I just want to sort of point to sort of examples of that, because seeing that that not all laws state regularities explicitly will help distinguish this feature, this connection between laws and space-time from the other one that I would like to mention, that I'll mention on the next slide. So just some examples. So there's the time-dependent Schrodinger equation, which has both space, which explicitly states its regularity in spatial and temporal terms. But of course, there's a time-independent version of the Schrodinger equation, which in explicit terms only is stated just using spatial derivatives. And or even more extreme, for instance, Chargaff's law concerning DNA, and that the amount of guanine equals the amount of cytosine, and the amount of adenine equals the amount of thymine. Okay, there's no explicit statement of space or time in that law at all. Okay, you may have in mind that there's some implicit space-time reference going on in this law, and I'll touch on that in the next slide. But the issue is just straightforwardly going to be, well, characteristic laws are actually formulated in space-time terms. So how are you actually going to formulate laws that at all if you don't have any space-time dependent degrees of freedom? Okay, so of course, one particular concern here is going to be, what are we supposed to replace dynamical laws with time-dependent laws with, if there is no time, if we're trying to think about a theory in which there's some laws, a theory in which this time isn't one of the parameters that we think is involved. Okay, so I'm just going to note here that, right, so this kind of question brings back, this issue about laws will bring us back to the question of what it is for there to be, what it could be for there to be change without time, if that's a feature of a theory. Okay, I'm just going to note, sort of just as an aside, that a similar problem, this kind of issue already arises in geometrodynamics as the problem of time, in which the Hamiltonian turns out to be a constraint and faced in various different ways. I don't have anything substantive, I don't have anything really at all to say about that today, except, I just want to note that if one were considering a theory of quantum gravity in which there literally was no time, that time was an effective notion, one would have to keep an eye on what one thought the solution of the problem of time was at the geometrodynamical level, and make sure one's conception of evolution in the fundamental level matched with one's solution to the problem of time. Okay, so, but the basic-ish first feature of laws then is that they often explicitly state regularities in space-time terms, and then there's going to be an issue of how to formulate laws in terms that don't invoke space-time if there isn't any. In a sense, okay, so the second problem that I want to distinguish from the first, the second, not problem, the second connection between laws and space-time is the following. So a couple of, again, sort of platitudes here. I said before, laws express regularities, but more specifically, they express regularities in what actually happens in occurrent events. Okay, they may do more than that, and there may be questions about exactly how they express those regularities. I've chosen a somewhat vague word there to make the point. But what's important is they tell us about what actually happens in the world. They're supposed to help us keep track of the things that actually happen, of actual occurrent events. Okay, so, laws may be telling us more. There are different understandings or claims about what a law actually is, and laws may be stating more than just this. But one of the things I think that all accounts agree with is that they're supposed to help us sort of organize exactly what not exactly, to help us organize the things that actually happen in the world. Okay, so what is it to be a current? What is it to occur, to be in a current event as opposed to a merely possible event, say? So I'm seeing a lot of questions appearing in the chat. I think I don't have time to answer kind of everything that's coming up unless I think it's really going to help clarify where the direction I'm going. But please do hold on to those questions and come back with them at the end. I'm very happy to address them. Okay. It's a little okay, anyway. So, but try to keep them to questions of clarification, okay? I think there are some philosophical issues that we can talk about at the end. Good. Okay, so here's an answer to what it is to be a current. And this is a sort of common idea, often associated with Aristotle, but others as well, which is that to be somewhere, and we might say to also be somewhen. That a currency that is, or at very least kind of requires occurring, it's spatiotemporal occurrence. You have to be somewhere and be somewhen. So if we put those two thoughts together, once we get to the conclusion, which is sort of itself a platitude probably, that laws express regularities in events occurring in space-time. Okay, seems like, it strikes me as a pretty obvious thing to say, but the reason I'm saying it is, of course, to connect the notion of law up to the questions of existence. That there's I want to emphasize in laws the connection between existence and location. So that's the point I want to make here. So one thing that, we notice, of course, and thinking back to the previous slide, you may have thought, as I noted, that there are sort of implicit spatiotemporal references there. And of course, that's right. So even in Chargaff's law, one thinks it's probably saying at all times and places or something like that, or quantify it, it's going to express some range in which the law is to apply. So that actually seems that even if a law doesn't, it seems right, if laws, generally speaking, have some implicit or explicit specification of where the regularities are instantiated. So they have the form at such and such times and places, L, the law holds. Okay, so, the most common thing for the such and such for XYZ to be is going to be at all times and places, but perhaps we want to hold open that there could be specific times and places. And I have in mind people maybe who propose that the past hypothesis is a law which specifies not things for all times and places, if I was going to formulate it, but for some specific time and place, namely the origin of the universe. Okay. So, but the general issue that I'm pointing at here is the question of what is an occurrent event or regularity going to be absent space-time? If we think that what it is to occur in space-time, what is going to replace this notion in laws, and what's going to replace this notion, and how is that going to affect laws in a context, if we find one in which there is no space and time? Things laws are supposed to be about things occurring, but there's nowhere or time for them to occur. What are we supposed to how are we supposed to rethink these issues or this picture in that time? Yes, I like a lot of these questions. I think hold them. Good. I feel I am. Part of my goal here is to provoke some questions here. I think I've seen questions here that I would very much like to come back to in discussion. At the moment, I want to kind of keep it at a certain level of generality, and then yes, these are all fair questions that should come back to. Okay, I am keeping an eye on the chat. Okay, but also being kind of mindful of the time. All right, So just to sort of recap, if we're thinking about these two issues, the first to do with formulating laws and the first to do with the laws being about current events, suppose we have a theory that's not fully spatiotemporal, could it really have laws? Well, I sort of see, so let's see, sort of 3 degrees of difficulties here that looks something like this. Well, I'm saying we're imagining a theory that's not fully spatiotemporal, but maybe it's spatiotemporal enough that we can have laws in pretty much like the standard sense. So perhaps we've lost space, or we've lost time, or we've lost some other geometric structure, but there's still a manifold, but there's still enough kind of vestiges of space and time to make these sort of familiar conceptions of laws work. And then it doesn't seem like we have, these issues are going to be fairly straightforward to resolve. I mentioned I excised a discussion of string cosmology, and I think the point I wanted to make in that example was, seems even in many of the sort of ways of thinking about what's happening at the Big Bang in those models, even if classical space-time has sort of does not apply, it's not an apt description, they still assume a background target space, which could play some of these roles of law for laws, I think. Okay, but I didn't talk about string theory, so I won't dwell on that point. The next level that we might be faced with is one in which there's not spatiotemporal structure, but the structure we do have is enough like space-time to allow us to sort of think about law analogs. We just sort of port over things we said about space-time to this new kind of structure. That seems most straightforward as an issue, as a response to the first issue that I mentioned. That structure would give us clues about how to mathematically formulate laws. It would be an analogy to the way we formulate spatiotemporal laws. But seems perhaps, well, it's still going to run into trouble with Aristotle's maxims, because we still can't have spatiotemporal occurrence. So one would want to have a question about what it is to be a current as opposed to merely possible. And maybe in this category, if the sort of existing approaches to string cosmology don't quite work, we may be driven away from target space and truly into M theory. Or the example that I want to talk about today, I think most naturally fits at this level, group field theory, which is what I'm going to talk about. But finally, there's a third level that one might think of where some there is nothing even like spatiotemporal structure. And the only kind of example I can think of that might be something like that is if we have a purely algebraic theory. Okay, maybe other people would want to put other theories into this kind of category. But if there's no even analog structure to space-time, then perhaps we might be faced with the idea that the very notion of law and the very notion of occurrence just don't really apply fundamentally, that these themselves are sort of effective notions, emergent notions that only kick in emergent space-time. Right, so I don't have examples of that. It's this sort of second level that I think the following example is going to address. So let me just say, so Carlo is asking, well, why should space-time exist independently from the events occurring? I don't think that let's ask that later. I don't think I'm trying to assume that. I don't think that's part of what I'm assuming here. What I'm thinking instead is a situation in which the events exist, but aren't existing in space-time. They're existing in some other structure. Okay. All right, so to my example, group field theory. So I've put in a citation to a paper by Daniele Oritti. So that's not the source of this, but this is a nice philosophical discussion of what I'm going to be talking about. Daniele, is one of the sort of drivers of and his group are the drivers of this program. I haven't checked through the attendees list. I think he's probably here. So let me just make a few comments about what follows. So what follows is, of course, my understanding of the work that he and his group have done. Okay, so, but I also want to acknowledge that he's answered recently, and actually over a period, and especially recently, answered a number of my questions about this with what I would describe as great patience and forbearance, and I'm very grateful for that. But of course, any errors that come in the following are my own and should not be attributed to him. I also want to note that this is going to be a very brief sketch of what's going on. And so there are many details sloughed over. Some of those details are going to be sloughed over because of my ignorance or error. Some are just choices I've made for brevity. But some are also because this is an active research program, and not all these things are settled, I think. So, but that's okay. That puts a slightly unfamiliar situation as philosophers, maybe, where we're more, often more used to dealing with a situation where quite a lot of the physics is already resolved and we're thinking about it. But entering that kind of context and engaging with physicists in active, in active research is very much what this project and my work at Pitt and this seminar is about. The thought that the physics and the philosophy need to be addressed together. So that's by way of justifying starting to talk in this speculative philosophical way about some physics that is under active development. I think those two things are need to be developed mutually. Okay, so brief background on group field theory. And the idea I want to have is I assume people are used to the idea of a quantum field theory over space-time, but this is a field theory where instead of a field over space-time, points of space-time, it's a field over elements of the group, of a group. So for instance, one might take the group to be SO13, okay, and actually 4 copies of SO13. And then one would imagine one would have a field in which, say, the phi dagger operator associated with a quadruple of elements of the group amounts to an operator that creates a quantum of the field at a point of group space. In the sense, the same sense in what attaching the same sense to that statement as one would to the interpretation of quantum field theory. Sorry to express some hesitancy about exactly how to interpret creation operators there, but that would be the the intuitive picture of what such a creation operator was. So we basically have quantum field theory, but it's in this group space rather than a manifold. So such quanta can then be pictured as nodes, say with 4 vertices, and each vertex then labeled by the group elements. And then these can be thought of as atoms of a spin network. Okay, so one of the ways of thinking about group field theory then is as a second quantized version of loop quantum gravity. Exciting and annihilating quanta of the field can be understood as creating spin networks, and so this is something like a second quantized loop gravity is how it's described. Okay, I'm not going to say too much about that's not going to be a huge point of this talk, but I'm going to I think there's two reasons to note this. One will become clear below when we start to talk about how to derive a space-time from group field theory. But the second one is this motivates, I think, much of the interest in group field theory that its relation to loop quantum gravity is one way of motivating why it's worth, why it's an interesting thing to study. Okay, insofar as loop quantum gravity is, group field theory is a way of getting at a similar formalism. Okay, I keep turning my page too fast. The story I want to tell now relates to the application of the renormalization group to group field theory. So obviously the renormalization group is a sort of a complex topic. So I'm hoping many of the people here are familiar with the basic ideas, at least as I can mention them here. For those that aren't, I'm just going to sketch things in very broad terms, of course. So the idea is, suppose I have an action with various terms in it. So those various terms are going to be generally parameterized by constants of the theory. And so, the classic, a standard example might be to think about a field theory with mass terms and coupling strengths. That's the kind of model to have here. Now, if there's a scale parameter in the theory, for instance, a cutoff or an external temperature scale, then the renormalization group will describe how those constants, in that sense, change under variation of the scale and determine a trajectory through parameter space, the space of the values of those different parameters. That's I think, about as much as I have time to say for the renormalization group. But an example of this that I think is a useful analogy for what I'm going to say is in quantum field theory. If you renormalize the theory, then you'll find that the renormalized couplings run with energy. So, for instance, if you have an asymptotically free theory, as the energy increases, the renormalized couplings decrease. If it's not asymptotically free, then there's a risk that they will blow up at some point at some energy scale. Okay, but the renormalization group helps explain and understand this scaling behavior. So now think about the parameter space. What one typically finds in parameter space is that it's divided into different phases. Okay? We have a phase diagram in parameter space, and the renormalization group, the study of flows under the renormalization group, will provide an account of these phase transitions, transitions from one of these phases to another. So, the standard example in solid state physics would be a transition from paramagnetism to ferromagnetism, for instance. But there are many other examples of phase transitions. So I say it provides an account. I mean, there's quite a philosophical literature on, and so I guess in physics, of what kind of account or explanation this is. It will, in fact, I think those questions will in fact be relevant for fully teasing out the picture that I'm about to describe. But for now, I don't have a lot to say about them. If people want to bring that up in discussion, that would be good as well. But of course, I think what I'm going to say here, with a nod to Pittsburgh's own Bob Batterman, is exactly what kind of account it is. Well, the devil's in the details regarding exactly how that works. Okay, so the example, though, that will be instructive, I think, for what's to follow is going back to quantum field theory again and the standard model. We have a running of couplings, the constants in the standard model, with the energy density, and so with the temperature. So when one thinks about unification, so the couplings change and there's a point where they come together. This is also associated with this change in the couplings, is associated with change in the theories that amount to a change in the vacuum state. And as the vacuum state changes into a degenerate vacuum, one can have the phenomenon of spontaneous symmetry breaking. So that's an application of these ideas that people may be familiar with. In the case in hand, it is this idea that the running of couplings can be associated with a change in the vacuum state. And indeed, that's the picture that is to be applied to group field theory. And the situation, as I understand it, is there are phases with a Fock vacuum, basically no particle vacuum, a no quanta vacuum. And there are other phases with a condensate vacuum, which basically have an infinite number of excited quanta, and that's associated with other regions of parameter space. What I understand to be more conjectured or to be studied, although some work has been done in this direction, is that there's a renormalization group flow that actually links them in the way indicated here, in the sort of standard way that I've just mentioned. Okay, so that's the basic underlying picture. Different phases, interested in group field theory, parameter space, and a renormalization group ideas applied to them, describing flows between them. Okay. So this, actually, sorry. I know it's annoying when people do that. At this point, actually, to these last ideas, I did also, I might want to give a comment in the direction of John Ehmann, who has written sort of extensively on these on the question of spontaneous symmetry breaking. In the first place, as I understand it, as a sort of static phenomenon, understanding, say, the Higgs mechanism. But I do also remember a few years ago hearing a talk from him, I think in DC, in Maryland, at one of Jeff Boob's meetings, also talking about the complications involved in what I've just talked about here in the idea of a vacuum change. I'm afraid I don't remember the details of the talk, and I couldn't find a version of it online, but I do think, I guess I really want to acknowledge that there are sort of philosophical interpretational issues in understanding just what's going on here and whether this, how good a picture this is. Okay. That's not special to group field theory. That's to, I think, the philosophical understanding or the conceptual understanding of exactly what's happening in this scenario. Okay, very good. But assuming that it does hold, I want to now talk to the key idea, geometrogenesis, the idea of the universe, space and time being born at a certain point. So here's the story. And I should say, this is an idea, that Daniele has sort of emphasized in the philosophical paper that I described, and as a feature, he's interested in pursuing this as a feature of group field theory. And although I don't think he's the originator of this term, there's a couple of earlier papers that talk about have this term. But the idea is, as it says, the origin of geometry. And how does that play out in group field theory? So the following, the condensate vacuum. Yeah. Thanks, Daniele. He's I remembered Bertini Marco Polo was in there. I'd forgotten that Lee Smolin was there. And I don't know, I'm not sure about Konopka. That's the original paper. So here's the description. So we've decided we've noted that there are two vacua in parameter space. One is a condensate vacuum, and that does have a description as a quantum space-time. And yeah, okay. And the other vacuum is the Fock vacuum, which doesn't have a description as a quantum space-time. So just want to give a little explanation of what I have in mind here. So this, the condensate vacuum then is a collective state, a state of many quanta. And so it we can a hydrodynamic limit can be applied, in which case we can we can describe the state in terms of its which allows one to describe the collective degrees of freedom, the behavior of the collective degrees of freedom. Essentially, applying that limit, you find that they satisfy a fluid equation, and that fluid equation can be interpreted as a wave equation on mini superspace. Okay, that it would have this interpretation shouldn't be too surprising given the connection that I noted earlier to loop quantum gravity. Okay, so that's the picture. We have the renormalization group trajectory from the previous slide. We also have the understanding that the Fock and condensate regions correspond to non-geometric and geometric phases. And so there's two senses of geometrogenesis. One is the, I'll say, stationary sense that group field theory parameter space contains both geometric and non-geometric phases. And then in the sense that there are sort of points just in the space of transition between them. But more robustly, there's a parameterized sense. One wants to sort of say a dynamical or sort of time-dependent sense, but we don't have time here, so I'm going to use the word parameterized instead, that there's a trajectory with respect to a varying scale parameter that connects the phases. I'm going to put scare quotes around connecting here because, okay, part of the interpretation of the renormalization group will say there can't literally be a trajectory between these 2 points. But that's one of the details I'm sloughing over at present. Okay, but this is the more dynamical, although because I really want to factor out assuming time, I'm going to say parameterized sense here. And so here's the proposal, which is, let me take a little bit of care here. This is essentially what Daniele is suggesting, but I don't think this, I don't know what degree of sort of assurity he wants to assert that. And I'm pretty sure that the exact way I'm going to put it is probably stronger than anything that he would say. But I'm going to put it in a fairly provocative and strong way for emphasis here, but quite willing to, I'm putting it as a proposal, so quite willing to kind of negotiate on the terms here, I guess. But here's the basic idea in stock terms. So fundamentally, the world, and by the world I mean what exists, is a parameterized renormalization group trajectory in group field theory space. It is one of those trajectories whose phase, and we're now kind of coming to the more tentative part, perhaps to signal the tentativeness of this point, transitions, the phase changes from a non-geometric to geometric phase, and that transition can be thought of as corresponding to the Big Bang. Okay, all right, so that's perhaps where you were expecting to come to at this point, given what I've said. So I see the clock is ticking down, so I'm very glad I cut that section, and maybe I will do maybe 2 more slides if people will indulge me with a few minutes over the 45. So first, how then could one actually see the emergence of space-time from such a picture? I've got a renormalization group trajectory through group field theory, parameter space. How does that correspond to the observed universe, the universe we actually find ourselves in? And as I understand it, again, here's the kind of story that Daniele wants to propose here. Okay, so first of all, we've already got in the geometric phase, we know that points of the renormalization group trajectory correspond to quantum spacetimes. Assuming that we're in a suitable regime of the quantum spacetime, one can then also take a classical limit to get a classical spacetime solution once one's in the geometric phase, at least for part. Okay. So getting to there's another limit to take here, but that will take us from the quantum space-time that we already noted to a classical space-time. Now, here's the sort of conjecture about what may be going on here to link these two things. And again, Daniele maybe can speak to, if he wants, to how conjectural this is. But the idea is, look, space-time, the classical space-time that we get, the quantum space-time even, the solution to the problem of time is going to be that there's a relational time parameter, some field, the volume, scale factor, some matter field, works as a clock in that space-time. That's the notion. That's an internal clock, an internal time. Call that field C. But that field has to correspond to the renormalization group scale parameter. Let's call it X. Okay, we've seen the renormalization trajectory is with respect to a scale parameter, and maybe there's a correspondence. Not a correspondence in the sense that these are the same thing, so that literally sort of X ticking off, moving along the renormalization group trajectory is a matter of relational time passing, but in this following sense. So, and this is kind of key to the emergence of space-time and embodies a lot of assumptions about how one would go from the underlying picture to observed space-time. So suppose we're interested in describing the universe at some particular time c, some value of the internal time parameter. Well, we get a good description if we take the classical limit at any point of the renormalization group flow, obviously in the geometric phase, providing that the scale of set by the scale of c is far above the scale set by x. So the analogy here is in solid state physics, if I'm interested in long range physics at some distance scale, it doesn't matter too much what I set the lattice spacing to be in the renormalization group, as long as it's much smaller than the scale I'm interested in, because that what happens beneath that scale is the long range physics is insensitive to it. So it's the same idea implying here the scale I'm interested in is c, so x has to be far that has to be far above x. Well, look, above and below are kind of just jewels here. I mean, if I'd been talking about momentum, then I'd want the momentum scale of the renormalization group to be far above the momentum scale of my process. So, but I'll just use above, as a handy word here. Okay, exactly whether it's above or below wouldn't something need to be worked. Would depend on the details. So that's how the internal time is to correspond to the parameter of the renormalization group flow and give it a sense in which it's time. Now then, if one's interested in seeking descriptions of ever earlier epochs, then that will drive the relevant, as c in this picture, as c gets smaller, say, since x has to be even smaller, then considering ever earlier epochs of our universe will drive the relevant renormalization group scale back towards the phase transition. Okay, and then the question is, what happens? Does it get all the way to the phase transition? But there's a certain sense in which one might want to say, well, look, if it pushes x, the renormalization group scale factor parameter all the way back to the phase transition, well, then it's actually there's a meaningful sense in which we can think of connecting that the trajectory back to the trajectory prior to the phase transition, and there will have been an earlier, in scare quotes, prehistory, non-geometric prehistory of the universe before, in scare quotes, epoch in which the universe was non-spatiotemporal. Okay, lot to take in there. So I'm going to rattle right through this, and I'm going to skip the last slide because I am over time now. Okay, so what do we kind of conclude here? Well, we've seen there's we have a fully non-spatiotemporal theory, both in the sense that group field theory doesn't have space-time in it. It has a group as its basic space, and in the sense that, in some sense, the world is this renormalization group trajectory through the parameter space of group field theory. In either case, the framework to me looks like it has sort of enough familiar structure that one is thinking about how to formulate laws, so thinking about my first issue regarding laws and space-time, that we're in the sort of second level of issues. And so one can, in analogy to space-time laws, think about how to formulate laws in these contexts. For instance, writing down a renormalization group equation that kind of looks like a dynamical equation, typically Aristotelian rather than Newtonian, but a dynamical equation. But it seems we are in the point that the situation I was pointing at, where, for instance, if we think of points of group field theory space as sort of possible stages of the world, there's a question about what is the difference between occurrence and non-occurrence? What is it for one of those points to be a part of the world rather than just a possible part of the world? So the question of occurrence does come up here. I think related to this is the fact that the renormalization group flow is often understood as a mathematical fact about parameter space, whereas here, and I've used the word empirical again, where perhaps I want to use contingent, but I'm shying away from that word a little bit here. How can it be a sort of natural law if it's really just a mathematical law? How can there be any physics here? And maybe the answer to that question is similarly tied to the idea that it actually is distinguishing occurrence from non-occurrence. The final thought I'm going to leave you with is, I asked, what should we replace Aristotle's ontological maxim with? Well, the obvious sort of fallback that people may be thinking of is Quine's ontological maxim, which is to be the value of a bound variable. This may be the route that one feels pushed to take in this theory. So we have laws in which the variables refer to time. We quantify over time or space, or in this case over say points or things that are happening in the renormalization group in parameter space. Quine's maxim sort of points in has two sort of features. One is it's a potentially much more generous about ontology, which seems to be what we want. We want to not have to assume that space-time existence requires space-time. On the other hand, of course, it's a thinner notion of ontology, I would say, and there are many understandings of what this maxim really means that range from really quite realist, I would say, to certainly the more positivistic, that this existence, becomes more positivistic. It just comes down to what our most sort of useful theories for reconciling the evidence are, and of course the question that the worry, perhaps it's a worry for some and not for others, is that does push one towards the sort of a relativity of a conventionality, a relativity of ontology, perhaps a kind of idealism if it depends on your cognitive capacities. Okay, I think in the interest of time I will stop here. I'm going to put up I do have one more slide which I'm happy to talk about. I have a sort of thought about I'll leave it up. People can also go to the chat if they want to pull up the handout and look at it. The point I was making here was to try to question whether we should put too much weight on the fact that the way we formulate laws seems to be closely tied to the notion of possibility, and that maybe we shouldn't be putting too much weight on that. I kind of wish maybe I'd heard the talk that John Norton is supposed to be giving on something along these of these topics that was cancelled last week, but that is promised for the future. But one way out of worrying about occurrence versus non-occurrence is to think about laws in a way that decouples them or de-emphasizes the role of possibility and what they say about possibility and necessity. And I had some thoughts in those directions. All right, maybe it would have been quicker to read the slide, but I don't think so. I'm just going to wrap it up there and say thanks to everyone for sticking with me for a little longer than I should have gone.
Excellent. Thank you very much. So please, if people have questions, alert me either through the Q&A or the chat that you have a question. So there have been some questions. Maybe we could start with those in the chat. I think Christopher Weaver had a question. Let me allow him to talk. Christopher, please go ahead.
Hello. Hi.
Can I just make a note before you?
Sure.
Just so people know, if you don't want to type up a question, just to emphasize again, it's fine to just put your name into the Q&A section, and then I think Chris will call you that way, and then you can just come and ask the question too. Yeah, Chris, go ahead.
Yeah, no, I mean, this doesn't touch on any of the major points you're making here toward the end, but the question was just about what you were saying about laws, and so you had said that laws should be about a current things, the current events, actual world goings on, so to speak. And I was just curious about whether you thought there were vacuous laws. And so some people think that the geodesic principle and general relativity is a vacuous law. Some people think that the law of inertia is a vacuous law, that strictly speaking, the antecedent isn't satisfied by actual world goings on. So just curious what you thought about that.
Yeah, I used the word, and maybe the fact, actually, this doesn't sound like a very Rutgers kind of question, actually, but I had very much the same thing in mind. And I don't think I got to note this when I was speaking, but I used the word express regularities with exactly this kind of case in mind. I don't mean, and I chose that word instead of state regularities, with just the thought that laws might in fact be vacuous in that way. That express is to mean as a sort of system, they help us organize the regularities that we find in the world. Maybe that kind of point, even puts too much pressure on, could even undermine that idea, but I didn't mean that they have to literally state regularities. I meant that as a system, they provide us with, I guess system is a way, a method and a system for actually describing the regularities that we find, even if it's true, some of these laws may be vacuous and so don't literally state regularities themselves. I think it's compatible with that's saying, the geodesic law is part of the system that helps us control, describe the regularities that we find. So I don't think that, and I think you're right, I don't think it bears too much from what I had to say afterwards. And so once I've said that, I kind of do, move to a picture where I'm sort of idealizing that they literally state regularities, but I do have that in the back of my mind. You also asked about the entities in Chargraph's laws,
right,
being spatiotemporal, and that that's what I had in mind in coming back. That yeah, of course, but that's sort of implicit. And I was just, when I was thinking about this, I would run together the two issues that I was sort of separating here, and just thinking of the laws being about a current events and not properly separating that from the idea that sometimes laws explicitly are spatiotemporal.
One quick follow-up, if I may, really quickly. So, I mean, there's sort of like a question that touches more directly on sort of the central issues you were raising. But that's related to this question about the natures of the quantities that enter the laws and how, and you're absolutely right. You did circle back and sort of say, well, yeah, implicitly, or even maybe when you want to give rigorous statements of these kinds of laws, you're going to write in something about how these things hold true at particular places at particular times. I'm curious as to whether, so first, I'm curious as to whether you think the laws of our endgame sort of quantum gravity theory are going to need to be not just useful for helping us organize regularities, not just useful for us in the sense that they help us unify, they explain perhaps in that sense, but that they're also approximately true, right? Verisimilitudinous in some sense. And if you think that that's the case, then where I get worried potentially is whether these laws are going to be such that they're going to appeal to quantities whose correct metaphysics requires a background of space and time, right? So in other words, my question is, if you think these laws have to be approximately true, do you think then that these laws are going to have to be such that they do not report on quantities whose metaphysical natures, so to speak, require time, require space-time?
Okay, can I please ask people to be pretty brief because we have a long list of people who want to ask questions. Thanks.
Sorry about that.
I guess that includes me. I mean, the brevity part. Yeah, no, that's great, Chris. So, yeah, I mean, in a way, this is coming at, it's related to the issue of occurrence that actuality that I'm bringing up here. I do, my inclinations are to be kind of broadly realist about quantum gravity. I do think it's right that the further you are, the further the claims of a theory are removed from, direct observation or experiment. Just as a matter of fact, the chain of inference is longer and the uncertainty gets greater. But I don't see that as sort of in principle argument against realism. So I do want to be kind of realist. So I think you're probably right. If one has a theory that, that's going to be susceptible of the kind of realist view that isn't spatiotemporal, then the quantities in the fundamental quantities can't be spatiotemporal. And then the game is in how one recovers spatiotemporal quantities from them. And in a sense, that's the book that Chris and I are writing on, trying to come to grips with issues like that, how one can meaningfully recover spatiotemporal quantities from something non-spatiotemporal. And it's not the loss, it's not giving the conclusion or the denouement of the book away to say that we have a kind of, functional reduction in mind here for how one would go about doing that. But there are a lot of questions to sort of describe, to answer there.
Okay, Carlo Rovelli, please.
Yes, can you hear me? Is that?
Yeah.
Okay, yeah, thanks, Nick. This is you raise a great problem, what the sense of law, if you're questioning, if you're generalizing about the notion of space-time. But I'm puzzled by how precisely you're putting your question here. When you use the notion of time or space-time a priori, as it was obvious, you start by introducing this notion of event, which seems wonderful to me and very clear. But once you have events, if you think that we can think about the world as a big collection of events, and that they are related by laws, then if you start talking about space and time, you have to say what it means, because it can simply mean the structure that this event sort of form together in a certain approximation. So if space-time, in the way, one way of viewing it is just a collection of the events that, for instance, in some approximation, if you disregard something, you can view it as a pseudo-Riemannian manifold, but this is an approximation. If you look at it more closely, it's not. But if it is not, you don't need to think about space, about time, about manifold, everything. You just have the events and a set of things that says what is this event and this other event imply another one of this event of the other event are likely to imply some other one. So in other words, why putting space and time first once you already have the full story and space and time can come in later?
Yeah. So let me work in this sort of, the parameter space for group field theory sort of picture. I take it in what you're sort of suggesting then, the events are then going to be in that picture sort of points along the renormalization group trajectory. So, I did in fact say, okay, those are events and that's the world. But I think I still, at least when I just say that, I feel that I'm not quite sure what I'm saying, that those are the events. And part of it is that I'm worrying about all the points of parameter space that are not on the this trajectory that correspond that is our world. Okay, and what exactly the difference is supposed to be between them, especially when I'm thinking about events and points in the non-geometric phase. So, and I think then there are I think people clearly have felt sort of similar sort of questions when we're talking about events in space-time or what existence is, and have been happy to, I guess that's the Aristotelian maxim, to just stop there and say, well, it's something in space-time and that it is an event in space-time and that's all there sort of is to say. And so maybe what you're saying is sort of extend that maxim, but into whatever the space is.
Can I interject?
Fair enough, but I'm sort of, that to me it feels as if when I first say that I've now moved from the context in which I really felt I had some handle on what I was getting at and what things existed and didn't exist, to a context where I don't feel I have the same handle. Now, I think I may be more in agreement with you that I'm coming around at the end of the talk than that sounds, because what I'm sort of suggesting is ways to be less worried about, existent, actuality versus possibility, and maybe that is in fact the solution. And if I can be cured of, that particular worry about what's going on in this context, then basically, I am on board with what you're saying.
Just one phrase: a human being. It's always a human being located in a family tree. But there aren't family trees without human beings, and what's the point of doing the deep philosophy about family trees? It's just human beings and the way they're related to one another. And there are some laws there. I mean, usually one has a mother and a father, at least biologically. That's a law, a different gender, different sex. But it comes after, not before. Why focus on a point on the renormalization group? The renormalization group is it's a scale at which you're looking something. So the events is not a point along the renormalization group trajectory. Renormalization group trajectory, a point is just an approximate description times scale of a set of events. The same in standard quantum field theory. But this is probably another direction. I want to take you to another direction. So we might be closer than what.
So, yeah, I'm not sure I totally agree with that. What's kind of going on here? That's quite how the renormalization group is to sort of be read here. That in some sense, what's happening along this trajectory is a real physical change, is the picture that's going on here, so that this is not purely descriptive, that this really is a history in some sense with respect to the parameter. I mean, I think this, really has to go. So there are real questions. I think the question here is exactly how to apply the sort of renormalization group ideas here. So that I do want to push it back to, there really is an actual phase change going on in the same way a system might go from paramagnetic to ferromagnetic. This is not just a sort of change of description scale. This is associated with a real physical change.
I don't want to take time away from everybody else.
But I do also like, I like the way you're thinking about the ontology sort of in general here. And maybe that what you're suggesting would be a good way of sort of thinking about this. It seems to me to rely on having a good grasp, to apply that strategy outside of a space-time context seems to me, I have to have a good grasp on what those relations are that are relating the points. So maybe this is another way of coming the problem, right? I like, the Leibniz family tree, and so you would maybe want to think of space-time in those relational terms. And I am certainly sympathetic to that, but of course that requires having a handle on what the relations actually are, I guess. And maybe that's another way of putting the question. That would be another way of kind of putting the question here. Exactly what are the relations that are involved between the existence in the geometric phase and existence in the non-geometric phase.
Right. I agree, and I think this is what the theory should provide. I agree with this.
And I think part of answering that question as well is to answer what is the what is the relationship between those relations and the more familiar spatiotemporal ones?
Exactly.
That we usually talk in terms of.
And exactly. I think that's the core. For me, this is the core of the question. Yeah. Thanks.
Okay, I very much like that way of putting it and thinking about it. Yes, thank you. Good.
Okay, Vasilis Sakaliario, please.
Yes, thank you very much for this talk. Can you hear me?
I can.
Okay. Thank you very much for your talk. Very stimulating. I have a simple question. What is the rationale of taking a group in order to construct your approach? And is the theory dependent on that in any fundamental sense? Would you take something more general, like a groupoid, for example?
So I'm afraid, okay, so, what I'm doing here is, as I said, presenting the work that Daniele Oritti and his group have done. So I'm afraid this is really a technical question that he may be able to answer better than I can. I think I don't know. I could fabricate an answer for you, but it seems I would just be kind of making up an answer like that. I certainly know this is not the only group that you can use. I don't know. I'm sorry, I don't have a better answer for you.
Okay, thanks.
Okay, Adam Becker.
Hi, yeah, I'm going to try to keep this short, and I apologize if this is something that's already been answered and I missed it because it's pretty early here on the West Coast. So I'm just trying to get my head around the relationship between X and C, and thinking about what that means for the past and the future as they relate to now in our usual way of experiencing time. So would this imply some sort of like block universe style thing where the past and the future sort of exist in the same way as the present because fundamentally time isn't a thing?
Sorry. Could you just say that? So I just wanted to bring the slide up and
it's okay.
Just
yeah. No,
the question didn't quite go in the direction I was expecting it to, given the preamble. So just
it's
say
okay.
the question
Yeah.
again.
No, I'm trying to just get a handle on this. So is this sort of implying, would this sort of picture imply that, the distinction between past and present and future in terms of, the present appearing more present, more real, is an illusion? Would this imply some sort of block universe where the past and the present and the future sort of all exist, and the distinction between them is not fundamental?
So that is the view I take of time. So
Yeah.
I'm sure it's naturally infusing what I've said here. And so, at least to that extent, I am presupposing that in the way I'm presenting things here. Is that a necessary kind of feature of this? So I hadn't thought about it a lot. In a sense, maybe what you're asking is, could one sort of read a version of presentism into this picture, or reconcile this with presentism in some way? Good. I mean, that doesn't seem very promising. Okay, good. For the following way. First is, if time is effective, that it seems the present, at least, and the common meaning of that is also effective, and so it doesn't really seem like one could tie existence to such a thing.
Yeah.
So if one were to try and read a kind of presentism into this, it would have to be maybe in terms of the x parameter rather than the c parameter. From my point of view, then, I think, that this is already a knotty enough kind of tangle of ideas that to add in which presentism doesn't seem to naturally sit. Maybe that's a mistake. And so, yeah, I haven't thought about how to insert any kind of presentism here. And I apologize for getting you up so early, and that kind of is my fault. When I was trying to figure out what time this should be in Pittsburgh, I kind of made a clock miscalculation that really messed up people on the West Coast, I'm afraid, but maybe made people in Europe happier. So it's hard to please everybody.
That's okay. It just means that those of us on the West Coast won't ask questions that are as good. Anyway, okay. Thank you.
Thank you. Dan Linford, please.
Well, thanks for the talk, Nick. This was really great. So I think this might relate to what Carlo Ravelli was talking about and to Adam Becker's question. And I'm thinking about what it might mean for an occurrence to be non-spatiotemporal, or there to be a non-spatiotemporal phase that transitions to a spatiotemporal one. McTaggart famously distinguished between like an A series, a B series, and a C series. And he thought that the C series was not a temporal series. So I'm wondering if maybe one way to make sense of these notions is by thinking about appending a C series to the front end of a B series.
Yeah.
I'm sorry, what was the question?
Yeah, no, and that was me trying to thinking about it.
Oh, okay, all right.
Since my answer to the last question was I hadn't thought about things in those terms, I was trying to avoid saying that again in answer to this question, but it happens to be true. But I'm not quite sure that is the way to. So maybe, but here's a reason to kind of resist that way of thinking. Is I do still have this my there is the scale parameter in the renormalization group flow, So I do have on the trajectory, more or less, but let me just leave out the more or less. I mean, I do have a parameter that sort of provides a quasi-temporal ordering. I mean, I have, I have sort of before and after in terms of this parameter increasing, say. So that doesn't quite look like the A series, a full C series, right?
But one way,
yeah,
I guess one way to,
I mean, maybe you want to say it's just structuring it by between or some between relation, but
yeah. I mean, maybe this just shows that it's at least conceptually feasible that you would have a non-temporal series transitioning to a temporal one.
Yeah, okay, good. So I don't know if that fits this example exactly then, but one could sort of imagine that in sort of non-spatiotemporal series, that there's some point in which the B series structure is emergent along the trajectory, but there are quote earlier regions along epochs in the history where that wasn't a feature. I don't think that's quite what's happening here, and maybe sort of for another reason, the time, if C is the time here, it's not C really that gets extended in any way, or whatever it is C is parameterizing is not what's getting extended into the non-geometric region. It really is a total fading of time at all, insofar as C parameterizes anything, except insofar as C kind of corresponds to this underlying parameter. But the underlying parameter is sort of this, seems to have the same status at any point of the trajectory. It's just that for some values of x, we have also this C parameter that is effectively the time that we see in the universe.
Thank you very much. Mike Schneider, please.
Hey, can you hear me?
Yes.
All right, so at best, this is hopefully an interesting question, philosophically speaking, and probing at part of your point on this slide. At worst, this is just hoping for some increased clarity on the formal construction or the physics. So the thing that I'm worried about in item C on this slide is that we are just like smuggling in a priori conception of time in the beginning when we, and then proceeding to say we can now understand relational time in terms of it. And it's essentially that we get to compare time C, its numerical value, say, to the numerical value of x, which on the sort of standard view I would think on the renormalization group is not really a flowing parameter so much as the way of picking out where along the trajectory you are. And so I'm worried that in moving to say we can compare the values of these two quantities, that's where we've introduced the flowy part of the parameter along the trajectory. And then that's just smuggling in an a priori conception of time.
I think the answer to that is that, C is a relational internal time. So the way I think about that, it doesn't have any flowy character either.
I see. So, sorry, I was, maybe my confusion then was trying to connect it up to the earlier and earlier epochs line in the conclusion there, where I get to move to, I guess I was thinking of earlier and earlier as the flowing backward.
Good. No, so, sorry, and I think I was going a bit quick. I was going quickly at the end for sure. and I've tried to put this in, the emphasis sort of is on description. I do feel I feel the issue that you're kind of raising here, and I was definitely trying to sort of punt on it to some extent here. So I'm kind of glad that you've kind of raised this. So I've put it in terms of just description. So the way I was just thinking about it was trying to put it here was, suppose I want a description of earlier and earlier stages of the universe. It's in the question of where do I find that description in my picture of the emergence, in this picture of the emergence of space-time. That would require one to look, appeal to earlier and earlier points of the flow. I have the word flow. Sorry, I see that there now. I just mean, I should have said trajectory there rather than flow.
Okay, so part of this is you're punting on the.
So I think if you want to turn this question then to what was the earlier universe or something like that, right? So my move here is to just talk in terms of where I find a description of what I see. That I sort of do feel the pull of a question about well, what was the earlier universe, not what would be a good description of it. But I was trying to punt on that a little bit. And again, I should have said renormalization group. I meant just trajectory here rather than flow. So go ahead, Mike.
That helps a good deal. I guess one of the lingering questions that I accept that you're just punting off for a different conversation, but I think is important in the cosmology context is we don't simply want the descriptions at various moments that happen to be behind us. We want some feeling that we've understood how all of those moments are stitched together, even if that's not flow, which might be a further thing. And the items on a renormalization group trajectory are too disjointed, is part of my worry, to hope to get an answer out by the end of the analysis. Does that make sense as a worry? Is there an immediate reason why I should just diffuse that concern?
So, yeah, no, I see. I think I understand the worry, and I mean, in a way, it is a technical question to which I don't know the answer. But I think the answer is that there is sort of, it is actually consistent. I don't know how well technically under control this is, but it is actually consistent to think in this way, that the stories I'm getting for later times are compatible with the stories I'm getting for the earlier times, even as one goes along the renormalization group trajectory.
I see.
So, okay, I think maybe I will leave it at that.
Yeah.
That it is actually connected enough that this works out. But I think that is, it is a question. Before you ask, I don't know if we must be running out of time as well. Before we go in, I just wanted to point out that if people are looking in the chat, Francesca gave a nice answer to Vasilis's question for me, and Daniele weighed in on that as well with some other answers if people are interested in that. And then I don't know if you were going to call on Lee or you just want me to say, of course, that's is Lee in your question line or?
Yes, he is, if he wants to be. Anyway, so the next one is Lisa Torzato, please.
Yes, thank you very much for the talk. My question is really short and fast. I want to ask you, what do you mean by emergence? Because you used twice. And I want just to ask you if there is any relation with the meaning of emergency of replacing the notion of dynamical laws. That's it. Thank you.
So again, there is quite a kind of literature on this. Ultimately, as I said, emergence for us, I'm not sure if I quite understood emergence, if you meant emergency in the sense of, something bad happened that needs to be fixed quickly. That's not a connection that I have here. Emergence for us is is in the family, perhaps a species of reduction, but in a looser sense that there is some kind of novelty involved in the higher level structure. In this case, space-time from non-space-time. Robust novelty, stable novelty, stable with respect to whatever changes within some of some degree in the lower level theory. And in particular, we have in mind, as I said, a kind of a version of reductive functional reduction. So that's what I mean by emergence here.
Okay.
Does that help?
Yeah, perfect. Thanks.
Okay, great. Next one is Daniele Oritti, please.
I'm muted. Yeah, I hear. Yeah, yeah, I'm here. Sorry.
Okay.
So I think that I would have something more to say about all the story, of course, of the relation between the possible relation between the RG flow parameter and the notion of time in a geometric phase. But I think Nick also explained the basics very well. So, I mean, I'm happy to discuss it more, but I think what he said is enough as a good basis. I want instead to ask Nick's opinion about the topic that I was never involved actively, so I just make apparent my ignorance. So in concerning laws, I'm trying to understand if the problems that you mentioned at the beginning concerning the notion of law and the fundamentality of space-time or lack of fundamentality of space-time are really, I mean, where they come from, how much the notion of space-time is actually necessary for the notion of law. I have two perspectives so that I see possible. So if I'm a realist about laws, then I must be, I guess, I must be a realist about the objects that constitute the ontology of the world and that are related by laws. Now, I think I agree with something that Carlo was saying earlier, if I understood it correctly, which is that I may have fundamental entities, say events or objects, depending on whether you take a relational perspective or a more substantival perspective on what underlies space-time. And then laws are just statements about the structural relations between these entities. In this vague, admittedly, but general definition, the notion of space-time doesn't enter directly anywhere. The entities could be non-spatiotemporal, and whatever I devise as the best account for the structural relations will be my laws. Then in any regime of approximation in which indeed space-time comes in as a good notion for describing the world, then those events may become located in space and time, or those entities may be located in space and time. And then the laws will refer to occurring events in time or actual experiences that we may have in space and time. But I don't see why the notional law will not admit a more general formulation that never refers to space and time. Unless, of course, you just define it as regularities from experiences, and then, okay, our experiences are in space and time, and so somehow there has to be space-time by definition. But then the very issue is resolved by definition. There cannot be a law without space-time by my very definition of law. That's one point. But this also suggests that the alternative viewpoint, in which you are an anti-realist, or at least a realist about laws, and you take a more epistemic type perspective on laws, could also a way to accommodate laws without any space-time. You know, as an agent, as an epistemic agent, you try to imagine the possible structure of the world in order to guide your experiences and your expectations for future experiences. And no, this expectation can well go, thanks to imagination, beyond actual experience in space and time, or actual experiences by the observer in the formulation, just like we do for atoms, for particle physics, until we manage to connect them to experiences in the lab. So I have to say that I'm still failing to understand exactly whether the problems in the notional law are basically there because we adopted too strict a definition or a very specific definition of laws, which is in fact not granted by anything. Thanks.
Okay. Yeah, great. And I certainly see the you're pushing in a similar way to Carlo on what I was saying. So, part of what I want to say. Okay, so first thing I'm actually going to say is, and this is maybe, well, one thing you might ask is, I only focused on regularities, and put to one side how this might bear on particular, philosophical conceptions of laws. And I mentioned that because I think Chris next week is going to at least start to address that question. So there may be specific ways that specific philosophical accounts of laws are more dependent on space-time, or more or less dependent on space-time, than the general notion. So the other thing is, I think I was careful not to call these problems. I chose, again, the word issue very carefully here. And I'm probably in more agreement with you and Carlo than the presentation perhaps, gave you rise to, indicates, in the sense that what I was really doing at the beginning part was, I think, sketching a fairly standard way of thinking about laws that's either implicit or explicit, and sticking and relating the idea of laws to some general, acknowledged or unacknowledged thoughts about, about laws, about possibility, about actuality, and pointing out how they could come under pressure in, theories, such as, group field theory. So the direction, maybe I'll just answer by sort of saying the direction in which I'm going is then, to try to relieve those kinds of worries by thinking about what might be, what might be wrong with those kind of intuitions people have, or sort of philosophical platitudes people have about laws, to think about how they should be thought of instead. I still think in that regard that what you just said and doesn't fully satisfy me, and maybe that I just need more kind of philosophical therapy here, doesn't totally satisfy me in this worry about what's the difference between the stuff that I've got a theory that has my laws and I have the sort of mathematical framework, and and as I said, I've sort of there's enough structure that I can write laws down. I can have a set of axioms, whatever, theory for the theory, and those are written down and I can formulate the theory. But I still seem to have, as it were, more possibilities than just the one actuality that I'm interested in describing. And I still feel the pressure of what's the difference between the actual and the merely possible here, and that some other kind of that had a link that I pointed out to space-time, and what I was starting to point to was ways about how that we might want to reject that link to space-time, as you suggest, and what might kind of replace it instead. Either just the sort of Quinean route, where we just have a different idea about the difference between actuality and occurrence, maybe, and possibility, or perhaps one just needs to see that distinction is not a very important one, sort of, at all. I hope that.
Okay.
Carlo posted a question to Daniele in the chat that maybe is a quick one. But I just wanted to say, since Lee put it in the chat, can I just address that one? He's quite right, and strictly the renormalization group, and I was gesturing at this at some point of some parts of the talk. strictly at a phase, as it were, at a phase transition, one finds a fixed point of the renormalization group, and so nothing can actually flow through it. And as he says, because it's an attractor, the renormalization group is really a semi-group, or I would say. There I was kind of gesturing to some of the interpretational discussion of renormalization group and how phase transitions are explained using what it actually means for renormalization group to give an account of or explain phase transitions, how that fact is addressed.
May I?
Okay.
Since phase transitions really do happen.
Nick, that wasn't my point.
Okay.
May I have a minute to say what the point was?
Okay.
This is from work of Kremers and Alain Cohn and much work in statistical mechanics. It's not just at fixed points. The renormalization group is not a group. I'll be brief. It's a half algebra, which means it comes and has to be understood within the context of intuitionistic logic. There is no inverse. There is another operation called an antipode, which on some portion of the generators acts as an inverse. There's not generally an inverse because there is no excluded middle. And so this is a deep thing. It's not an accidental thing. And it gets in the way or enhances deeply your notion of the analog to time, because it gives you a kind of one-way time, which maybe is not a bad thing. And it fits the issue of the role of time in quantum physics and cosmology within this interesting framework of intuitionistic logic. And this again was from works of Kramer and Cohn. And to mention her again, it was Fotini Markopoulou in a series of papers that made the connection to issues in quantum cosmology and so forth.
Okay, thank you.
Great, thanks. We have, sorry.
Yeah, no, okay, that's great. And I will look that up. I don't think the story I was telling necessarily requires the ability to literally, okay.
No, it's a good story, and there are a number of examples. There's a lot of studies under the name of the holographic renormalization group, which gives you detailed versions of this story, and I think it's a good story. And it's definitely, I think it's a good thing that you're following up on it. But it's a more interesting story than appears at first.
Okay, good, thank you.
Great, thanks. So we have two more questions. I hope we can be brief here. Vitaly Prostik, please.
Thank you very much for your talk. I have a very brief question, just for understanding, for clarification. Do I understand correctly that you mean that if we understand physical vacuum as a Fock space in Fock vacuum, this Fock vacuum cannot be non-spatiotemporal? It doesn't fit your proposal.
So I'm not quite sure. Okay, what you have. So what I had in mind here is, it's literally the state of nothing excited. So it is just the unexcited vacuum, whereas the condensed, the condensate vacuums is relative to that vacuum an excited state. You would think of it as a coherent state in which sort of every mode is excited. So when I'm so this is what I understand, and again, I don't want to speak for, maybe I may have misunderstood what Daniele was saying, but I understand this to be a sort of state of no excitations in terms of the, so I'm thinking of the Fock space in terms of, states excited by these excitation operators. Does that help? I was understanding your point to be that the idea of a Fock vacuum is tied explicitly to space-time.
Yes, I wanted to understand how this Fock vacuum is consistent with your discussion of non-spatiotemporal approaches. It helps, yeah.
Okay, and you can see the papers by Ariti and the collaborators probably for some more specific answers there.
Okay, we're actually over time, but for one final question, Shaheen Kaveh, please.
Thank you. Can you hear me? So I was wondering, when you talk about the renormalization group in this quantum space-time, quantum gravity theory, you talk about transitions, phase transitions and things like that. What do you mean by transition? There's nothing happening, right? There's no time. So what is a transition?
So I think I'm just going to refer maybe to this. I mean, I guess through, three things. First, there's just this stationary sense that there are different phases. So one could there's just boundaries between them in the parameter space, and one can call those transitions. The second, that if one has, a renormalization group trajectory, then one has lines modulo the point about fixed points that I was talking about, connecting the phases. Okay. Then, of course, you're coming to the question about, well, how is that a transition if there's no time? And I guess that, in a sense, it, just is the kind of question that that's being asked here, is what, in what sense is this time? Is this in any sense time? Is this in any sense a parameter with respect to sort of actuality or something like that, to put it in rather uncomfortably ponderous terms? So I think the question you're asking is in the family of questions that I'm asking here, would be answered by having a better sense of what laws and dynamics actually are in this context.
All right, thank you very much. I think we've come to the end of this meeting, so please join me in thanking Nick once again. Some virtual applause for his talk, and we hope to see you next week when our series continues. Thank you very much.